So in this video, we're going to be going more into finding probabilities from the normal distribution. So if we have a random variable x that's normally distributed and we know the mean and standard deviation, then we can convert x to a z-score by doing x minus the mean over the standard deviation. This formula to get the z-score. And then we use the standard normal, that chart, the z-chart, to get the probability, to find the area. Remember, area equals probability. That's how I want you to think about area and probability. They're the same. Okay? So, let x be a random variable that's normally distributed with a mean of 70 and a standard deviation of 20. I want to find the following probabilities. Look, guys, if you go and you try to find 95 in your z-chart, guess what? You're not going to do it. There's no 95 in the z-chart. So let's go to our tables. I'm going to pull up a standard normal. The smallest number looks like negative 3.49, and the biggest number looks like positive 3.49. So guess what? It is not big enough to count that 95 into it. So you know you got to do something to it. So how do we handle this? What are we going to do? We're going to take our value, we're going to subtract the mean and divide by the standard deviation. So 95, subtract the mean, which is 70 here, and then divide by the standard deviation, which is 20. And if I do that, then my x minus my mu over my sigma, I have to do it on both sides so that it's the same, right? This becomes replaced by the z, because that's the definition for the z-score, which is less than. And now type that in, 95 minus 70 divided by 20, you get 1.25. And if I go look up 1.25 in my z-chart, what am I going to get? 1.2 is here, and 1.25. So what is it? 0.8944. 0.8944. How do I know that I don't have to do anything with it? If you draw the picture, you can look and you can see that it's left tail area. Remember, 0 is in the middle. 1.25 is on the positive side. That's 1.25. This tells me I want values that are less than it. How do I know which way to go? It's pointing to the left. So which way do I shade? I shade to the left. Area in the table is cumulative, meaning it's area to the left. So that's exactly what you're looking for. So this is my answer right here. Okay, what about this one here? Let's try this out. So now I want to find the probability. And then 52 is not in there, but what I can do is I can convert, same thing. I take x minus the mean divided by the standard deviation. And so this has got to be greater than x minus the mean divided by the standard deviation. So that gets me a z-score, which is, if I type that in my calculator, negative 0.90. If I go look this number up in the chart, well, that number up in the chart tells me that it's 0.1841. Well, guess what? 0.1841. If I draw the picture, 0's in the middle. The negative 0.9 is over here. This number right here is area to the left. Okay, that's area to the left. That's 0.1841. Is that the area we want though? What does this arrow tell me right here? This tells me that I want z to be greater than or equal to, so that's area to the right. How do I find area to the right? I have to use the complement rule. This is 1 minus that number. And so area to the right, okay, is the complement rule, 1 minus. And so this is 0.8159. 0.8159. Okay, so this is my answer. All right. So you look area to the right versus area to the left. Okay. The arrow tells you which way you're going. Right tail area, you have to do the complement rule to get this blue area over here. That's the only way to do it was with the complement rule. All right. Now, this one, remember, we've got to first convert to z-scores. So 65 minus 70 over 20, and then 85 minus 70 over 20. What are these numbers? This is negative 0.25, and this is 0.75. Okay. So what do I do here? I'm going to take the probability that z is between negative 0.25 and positive 0.75. Okay? And so I need to look up in the chart these two numbers. If I look up in the chart those two numbers, so 0's in the middle, negative 0.25 over here, and 0.75 over here. So I'm looking for that area between the two curves, okay? So if I look up the 0.75 number, I get 0.7734. And if I look up the -25, I'm going to get 0.4013. And so what do? I subtract the two, because if they both give me right tail area, then to get rid of that area I don't want, I have to subtract it out of there. And so when I subtract the two, I get 0.3721. All right. Let's do an application. Same type of problem as this, only now we're going to do an application. Okay, a landowner claims that the pine trees on the land has an average circumference of 8.5 feet with a standard deviation of 1.2. Assume the circumferences of the trees are normally distributed. Good assumption. What is the probability that a randomly selected tree has a circumference that is, and then we've got three scenarios: less than 8 feet, more than 8 feet, and then between 8 and 10 feet. Sorry, more than 10 feet was the other one. Okay, so we use the Clark way for the word problems. First thing I do is I highlight my numbers. And anything else? Any others? Okay, here, and then here, and then there, right? Those are all my numbers. Okay, so what do I need to do this? Well, I need the assumption that it's normally distributed. If it's normally distributed, I need a mean, and I need a standard deviation. Well, guess what? There's only two numbers that I've got, right? So average is my mean. That's 8.5. Standard deviation, that's the standard deviation, 1.2. Bingo, we got it, okay? So now what do I want to do? I want to write this out. What is the probability? So when I see what is the probability, I automatically turn that into P of parentheses, okay? So P of something, that's what is the probability. How do I say this? Less than 8 feet. Well, I got to define a random variable, okay? So define a random variable. Let x be the number of feet circumference of the tree, right? Let's just say circumference in feet of the tree, all right? So then I would say x is less than 8, okay? Here I would say probability x is greater than 10. And then between 8 and 10, this would be x is between 8 and 10. That's how I would say that. So that's how I turn this sentence into a mathematical statement. Now I don't have any z charts that have 8 or 10 in them, so I've got to convert this. I got to standardize. That's the trick, guys. Got to standardize. Convert it to a z-score. Convert to a z-score by doing x minus the mean over the standard deviation. That's the trick. So 8 minus the mean, 8.5, over the standard deviation, 1.2. What is that number? That number, let's do it in our calculator. 8 minus 8.5 divided by 1.2. That's negative 0.41666666, right? So negative 0.41666666. Now, here's the problem. Our table only has 2 decimals, so I've got to round to 2 decimals. 5 or more, raise the score. 4 or less, let it rest. So this is going to be probability that z is less than negative 0.42. We round up because 5 or more, raise the score. 4 or less, let it rest. Now, this is a probability that is a left tail. How do we know? Because it's less than, it points to the left. So I shade to the left here. So all I have to do is go look up negative 0.42 in my chart. And if I do that, I find that it's equal to 3372. Okay, so that is the probability that it's less than 8 feet is about 34%. Okay. Next up here, I need to convert this to z-score. 10 minus the average of 8.5 divided by 1.2. This number is 1.25. So I'm going to do the probability that z is greater than 1.25. If I draw this in a picture, what's going on here? 0's in the middle, 1.25 is over here. Greater than tells me it's area to the right. Okay, z values that are greater than are to the right. All right? So what does that mean? That means I have to use the complement rule when I find this number in my chart. When I find this number in the chart tells me the number is 0.8944. Would it even make sense that 89% is over in that red shaded area? No, because not even half of it's over in the red shaded area, right? So this is the side that has the 0.8944 to it, okay? So that's all that it is for that part. Now, to get this side over here, what do? We do 1 minus 0.8944, and that gets us 0.1056. 0.1056. Okay, between 8 and 10 feet, well, you can either reinvent the wheel and find out the z-scores again, or you can just use what you found up here. When I standardized 8, I got the z-score here, that negative 0.42. And when I standardized 10, what did I get? I got 1.25. So I got the 1.25 here. So the z-score is between those two values there. Now when I look at the picture, what's in the middle? 0. So one of them's over here, negative 0.42, and one of them's over here, 1.25. I want to find that area between the two. Okay, how do I do this? Well, I find the z-score for each one that corresponds with the probability here. The 1.25 has a probability of 0.8944. The negative 0.42 has a probability of 3372. So if this whole thing here is 8944 and this little piece here is 3372, then to get the red circle in here, okay, all I have to do is subtract those two numbers. So this is equal to 0.8944 minus 0.3372. And if you're having trouble figuring those out, you just go back to the video where I talk about finding the area between curve on the z-scores on the standard normal. Okay, and that video will explain more of why you subtract the two to get your answer here, which happens to be 0.5572. Okay, so so you could tell your landowner that there's about a 34% chance that you've got a tree that's less than 8 feet. There's about a 10 or 11% chance that it's more than 10 feet diameter, or I'm sorry, circumference. And then most of your trees, more than half of them, are between 8 and 10 feet, is what this plot of pine trees is like, okay? So out of 200 randomly selected trees, about how many would you expect to have a circumference more than 10 feet? Well, the probability that your circumference is greater than 10 feet, we worked through that math already, didn't we? We standardized this, so we got a z-score of I guess it was 1.25, right? And then we figured that out to be about 10%. So about 10% of the trees are more than 2 feet, but if you got 200 trees, to find that expected value, all we have to do, is multiply how many there are times the probability of success, right? Your NP, it's a binomial. If you think about it, it's kind of like a binomial distribution. You're either greater than 10 feet or you're not greater than 10 feet, right? So all you have to do is multiply how many there are, 200 trees, times the chance that you are greater than 10 feet. That's 10%, 10.56%. And then whenever I multiply that out, I get 21.12. So about 21 trees. About 21 trees. That's how many you can expect to have a circumference greater than 10 feet. About 21 trees.